right there, AP Chem scholars. Let's go on to section 2, Intro to Rate Laws. Ooh. All right, so what is a rate law? A rate law expression is a statement of the rate of a reaction. We talked about rates a little bit in the last section, right? Okay. But we're going to focus on initial rates, okay? So how fast a reaction goes then depends on the reactants, right? Because we don't have products yet. So it's all about getting those reactants together with enough energy, with the right geometry, etc. Okay? So when we talk about rate law, we're focusing on the reactants. Okay? So a rate law expression is just that. Okay? It's a statement of the concentration of reactants and how much influence they have on the rate. And I'm going to explain that idea of influence. Okay? So it is a multiplication aspect where we're taking a constant for the reaction and the concentration of each reactant. So if there were three reactants A, B, and C, it would be constant times the concentration of A times the concentration of B times the concentration of C. However, their exponents, their coefficients in the reaction will be important, because if I had three C's, then and I'm multiplying, that would really be A times B times C times C times C. So it's really C cubed. So coefficients become exponents in these rate law expressions. Okay. Now, when we talk about concentration, obviously from a solution point of view, the most common way to talk about it is molarity. From a gas point of view, the most common way to talk about it is pressure units, atmospheres being the most prevalent. What about for solids and liquids? Well, solids and liquids are not compressible, so we don't really talk about their concentrations because they have fixed concentrations. It's essentially their density. Okay. So since they don't change, that means that they're constant. So we don't include them in the expression. They get included in the constant. Okay. So whenever there's solids or liquids, you can expect them not to be part of the rate law expression. All right. I know a lot of wordiness there. Let's take a look at something. So here's a reaction for synthesis of hydrogen chloride. So we see our reactants are hydrogen and chlorine. So in theory, the rate law for this should be rate equals K times concentration of H2. We use square brackets to indicate concentration times the concentration of Cl2. That's it. That's all there is to it. Their coefficients are 1, so we would have 1s, we don't have to worry about raising it to a power or anything like that. The constant K is very specific to the reaction and the conditions, especially temperature of the system. We're not going to deal with different temperatures, okay? But you do need to know that it would vary with temperature. That is something that does get asked every so often. So just keep that in mind. It is a constant. Okay? So if we knew the actual concentrations of these, we could substitute in. If we knew K, then we're going to find our rate of reaction. Okay, so that's what we mean here by rate. We're saying what the rate of reaction is at the start here. Now, I did say on the last slide that it was a theoretical model. And the reason why it's theoretical is we don't know what the rate determining step, or if this is an elementary reaction where it's happening pretty much in just one step. And that last one may have been elementary. It may have been in one step. We don't know that without seeing a mechanism, okay, without knowing the rate determining step. So we're going to talk initially about theoretical, but then we're going to actually move into the rate actual, or what's called integrated rate laws in a moment. So with that in mind, let's look at these and talk about what is the theoretical rate law. Okay, now remember, we said a couple things. First of all, we're only talking about reactants. Okay, so the products are not an issue for our rate law right now. Okay, so only the reactants. And we also emphasize we do not include solids and liquids. So iodine, you're out of here. All right, so if we do that, we should have, for this one, just rate equals K times concentration of hydrogen. For the water reaction, we're going to have rate equals K times concentration of hydrogen squared times oxygen. And for this one, the combustion reaction here, rate equals K times concentration of ethane squared times concentration of oxygen to the 7th. So I want to talk about those exponents for a moment because they're referred to actually as order. So looking at this reaction, I see that the ethane has an exponent of 2, oxygen has an exponent of 7. Okay, we refer to that as their order. So we would say that ethane is second order, oxygen is seventh order. And we could add them up and talk about the reaction order. So the fact that 2 and 7 is 9, this is a ninth order reaction. Okay, so let me talk about the reaction order briefly, and then I'll come back to the reactant. The higher the reaction order is, the more complicated it is. And that's logic. I mean, we're talking about taking 2 ethanes and 7 oxygens and putting it together. A lot of stuff has to happen. So the fact that it's ninth order is saying this is more complicated. It's probably got a bigger mechanism. Okay, things with lower reaction order are simpler, so they have a simpler reaction mechanism. But let's go back to talking about the reactants, because it almost sounds like I'm going to contradict myself here. When we talk about the reactants, the higher the reactant order is, the more important it is to the rate. Since ethane is second order and ethane is second order and oxygen is seventh order, oxygen is going to have a much bigger influence on the rate of the reaction than ethane would. Okay, and very specifically, and I'm going to show you this numerically in a moment. If you double ethane's concentration, the rate is going to go up by a factor of 4. Well, that's nice. But if you were to double oxygen's concentration, the rate would go up by a factor of 128. That's a huge difference. Oxygen is going to have a much bigger impact. All right, let me explain where those numbers came from real quick, though, and shift views here. So we were talking about the fact that ethane is second order, oxygen is seventh order. Okay? So let's just call this situation 1. So rate 1, we get that. Now, let's double the ethane. So we're going to say for our second rate, that we're going to have 2 times the concentration of ethane. But we're going to leave the oxygen the way it is. Okay? Well, since I'm doubling this, keep in mind that's 2 squared. Okay? So that means 4. So if I pull that 4 out, I would have rate 2 equals 4 times K times C2H6 squared times O2 to the 7th. And this, what's in parentheses, is this, right, which is rate 1. So that means that rate 2 would be 4 times rate 1. Now, I don't usually go through all this math. I just look at this and say, all right, if I double this, 2 squared is 4. That's it. But I'm explaining it from a math point of view to you, okay? So obviously then, if I talk about rate 3 real quick, and talk about now doubling the oxygen, we're going to leave the ethane as it is, but double the oxygen. Now I have 2 to the 7th here. Okay, 2 to the 7th is where I got that 128 from. So I have rate 3 equals 128 times K C2H6 squared times O2 to the 7th. And again, this is this. So that means that rate 3 is 128 times rate 1. Okay, so obviously oxygen is much more important. So when we talk about reactant order, that's where we're focusing is on just as an element, which element is having a bigger impact on the rate. The higher the order, that's the one that you want to increase. Okay, if we're doing a reaction, you know, and we talked about the fact that most reactions have an excess and a limiting reactant, it would make way more sense to have oxygen be the excess reactant if my purpose is to make this reaction go faster. If I wanted to go slower, well, then maybe I want to go the other way. All right, let me shift views again and go back to where we were. All right. So now that we got the theoretical model out of the way, let's talk about how we are actually going to find the real rate law, non-theoretical, okay, what is called integrated rate law. So we need laboratory data, or we need more information to know what the mechanism is. We'll talk about it from a mechanism point later on in the unit. Let's talk about it from an experimental data point of view. So what we would do is we would collect data, we'd run this reaction, and we would vary concentrations and see what happens to the rate of the reaction. So I could, start with some generic values, so 0.25 molar for each of them. I measure my rate. And then I'm going to modify one variable at a time. So now I modify the hydrogen, leave that alone, and I see that the rate changed. Good. Now I'm going to manipulate the other variable. So I notice that in the third trial, I leave the oxygen alone, and I change the oxygen, and I see that the rate changed again. So now I should be able to pull that out and be able to actually look at the rate law differently. All right? So we don't know. Theoretically, we expected this to be second order, this to be first order. That was what we talked about in one of the previous questions there. We don't know what it is, okay? So what you're really thinking about is this as our model, okay? And we're trying to solve for X and Y, okay? We want to know what is the power or order of hydrogen and what is the power or order of oxygen. You want to isolate variables. Remember I said that when we're running the experiment, you only change one thing at a time, all right? Because you want to make sure of which compound is having an impact on the rate. And if I change both of them, I don't know that. So when we compare the first and second row, the hydrogen changes, but the oxygen doesn't. So this change in rate has to be due to this change in hydrogen. Now again, I'm going to show you the long way of looking at this first, but I'm going to simplify it down. So let me move myself out of here. Okay. We have our generic rate law. I know from row 2 that the rate is 2 molars per second. Hydrogen is 0.5 molars. I'm going to leave the units off for a second. Actually, let's just even take it out of here for the moment just to avoid any confusion. Don't know why I'm getting that echoey effect here. Weird. Oh well. Ah, there it goes. Okay. Anyway, so the hydrogen was 0.5. The oxygen was 0.25. Now, if I take the data from row 1, the rate was 1, hydrogen was 0.25 molar, and oxygen was 0.25 molar. So now I'm literally going to divide these two equations. 2 divided by 1 gives me 2. K divided by K cancels out. 0.25 to the Y divided by 0.25 to the Y cancels out. 0.5 to the X divided by 0.25 to the X gives me 2 to the X. So now I have to solve this. Well, I'm not brain dead. I know that X has to be 1 if 2 is going to equal 2. So I know X is 1, and that means that hydrogen is first order. All right, so now let's talk about it from the oxygen point of view. So I go back to this. Now, I could take out the X if I want at this point because I know that hydrogen is first order. I don't have to worry about that, but what the heck, we'll do it. So now I want to compare the next 2 rows because in the next 2 rows, the hydrogen is constant, but the oxygen is changing and having an effect on the rate. Now, I always start with the bigger numbers first, so I'm going to do row 3. I'm going to take my 4 molars per second. Again, I think I'll just pull out those units just to simplify this for the moment. Okay. And so the concentrations were both 0.5. And row 1 was the same thing that we had before. Row 2. We had same thing as before, 0.5 and 0.25. So now again, I'm going to divide. 4 divided by 2 gives me 2. K divided by K cancels out. 0.5 divided by 0.5 cancels out. But 0.5 to the Y divided by 0.25 to the Y gives me 2 to the Y. So clearly, Y is 1. And again, that means that oxygen is first order. All right, so let me simplify this down, though, because I told you I do this in a much shorter way. All right, let me grab my draw function here. Whoop, come on. What I do is when I see that I have 2 rows where the data is relatively, one thing is constant, all right? So I'm just going to ignore this and this. And I'm going to say that this is my Y. Okay, so I divide these two numbers. So I just come right in and say, all right, what's 0.5 divided by 0.25? 2. So that's where I'm just going to say, all right, that means I have 2 to the y. And what's 4 divided by 2? All right, well, that's 2. So I get to that equation over here that I did way shorter than doing all this stuff. Okay, that's just the way I normally approach it. And on an AP question, this is typically a multiple choice, so you don't want to necessarily be writing out all that. I'm just trying to, again, explain the theory first to you here. All right, so don't feel that you have to do the long way. By all means, go to the short way. All right, so hydrogen was first order, oxygen was first order. So the rate law, the integrated or actual rate law, is rate equals K times concentration of hydrogen times concentration of oxygen. All right, in the theoretical model, we thought hydrogen would be second order, but it's not. Oh, okay, so that even would give us more information about the rate determining step, but we're not going to go there yet. Since this is first order and this is first order, I could say that this reaction is a second order reaction. All right. But we're really not done because we still can pull out more information and find this K that we're talking about. So now that we know this is our rate law expression, we can pick any row of the table we want, substitute in, and solve for K. So the rate was, I took the first row, 1 molar per second, equals K times 0.25 molars times 0.25 molars. All right, so this is 1/4, this is 1/4. If I take 1, divide by 1/16, I get 16, okay? Now in terms of units, I'm taking molars per second, dividing by molars, so that means this 1 molar here, actually let me do this, so this cancels out with this, but I'm still dividing by this molars here, so I'm going to end up with just over, so basically the units are 1 over molars per second. On the AP, they're big on writing it in this format in terms of reciprocals, saying 16 times molar to the -1 seconds to the -1. There is another way to think about the units, though. Okay. And I don't understand why, because when we go to equilibrium, we're going to start ignoring units, but with kinetics, it seems so important to them. The units always follow a pattern here. It's always 1 over the concentration units to the order -1 times time units. Okay, so think about that one. We said that that last reaction was second order, so 2 minus 1 is 1. We said the concentration was molars, the time was seconds, so I have 1 over molars times seconds. Okay, so that's really where the units are coming from. Well, really, the algebra is where they're coming from, but this is a way that will work all the time too, so you can always figure out the units that way. All right, let's go through one more quick example. I invite you to pause it, give it a shot, but I'm going to go on. So I look at the data real quick, and I'm analyzing from here, and I'm saying, all right, I see that the in the first row, the nitrogen is not changing, the hydrogens are changing, the rate is changing. So I'm going to look at these piece of information first. So, I skipped this step there. All right. So actually, let's just talk about it here. So doing it the way I was explaining before, I'm going to take 1.32 divided by 0.033, okay, and I get 4. And I'm going to say that's 4 to the y or 4 to the x. Well, we'll call this x and this y. All right. So now I divide 28 by 1.75, and I want to say 16, 1.75. Yep, 16. So when I divide here, this and this, I get 16. So now I have to say to myself, 4 to the y equals 16. What does y equal? Well, I know 4 squared is 16, so obviously y is 2. So hydrogen is second order. Okay, so here I am explaining the same thing. Okay. So I know hydrogen is second order. All right, so what about the nitrogen? All right, let's backtrack. So let's compare the first, let me actually click off on some of these things, clean this up a little bit. I really just pause this while I'm cleaned up. I'm going to compare the first row and the third row because I see that the hydrogen does not change. So now I'm going to divide 0.375 by 0.125 and get 3. That's an ugly 3, but you get the idea. 3 to the x. And then I'm going to take 1.75, divide by 1.75. Well, I can do that in my head. That's 1. So now we know that 3 to the x equals 1. Well, 3 to what power is 1? Well, anything to the 0 power is 1. So that means that nitrogen is 0 order. Why? Well, look at the rate. What happened when we changed to nitrogen? Nothing. Nitrogen is not affecting the rate of this reaction. It is possible for reactants to be 0 order because they're not in the rate determining step. Now, okay, does that mean that, that's going to happen all the time? No, we didn't see it in the last one. It just will happen. So keep that in mind. So that's now what's going on here. Again, I showed that it went up, although didn't the nitrogen went up by 3? 3, not 2. All right. Anyway, so let's now go back and finish this. Okay, we have to pick a row and substitute in. So, I don't know that one set of numbers is nicer than any other one. So let's just take the first row. Okay. So my rate was 1.75. My concentration was 0.033. Remember that this was second order, so I have to square this. I get around 0.00111. I divide out. I get roughly 1578. Now, in terms of the algebra of the units, I'm taking atmospheres per hour, dividing by atmospheres squared. So one of the atmospheres are going to cancel out, but I'm still going to have an atmosphere down here. But if you think back to that generalized formula I talked about a moment ago, okay, we have a second order reaction again. 2 minus 1 is 1. Our concentrations this time are being measured in, atmospheres, and time is being measured in hours, okay? So that's where those units of 1 over atmosphere hours come from. And again, on the AP, they would probably write it as equals 1578 atmospheres to the -1 times hours. Oh, nope, wrong button. Now, I will say this, okay? A lot of people always assume that time is going to be in seconds, and they end up getting easy questions wrong because of that on the AP exam. Always make sure of what the time is being measured in. Some reactions happen in hours, some happen in days, some happen in minutes. Okay, so always make sure the time unit. Please don't assume that it's just seconds. All right, so that's it for this section. Go forth and be happy.